Welcome back, everyone. Today we aren't just reviewing formulas, we are revisiting a crime scene. The late 19th century. At that time, physicists felt pretty good about themselves. They had Newton governing motion and gravity. They had Maxwell governing electricity, magnetism, and light. The universe felt like a perfectly predictable, giant clockwork machine. Some even suggested there was nothing left to discover, just more precise measuring to do. They were wrong, dead wrong. A few stubborn experiments just refused to obey the rules of classical physics. These weren't small errors, they were catastrophic failures that threatened to tear down the entire edifice of science. Today, we are revising those failures and the desperate, brilliant solutions that gave birth to quantum mechanics. Let's dive in. First up, blackbody radiation. This is the problem that started it all. A blackbody is an idealized object that absorbs all radiation hitting it and re-emits it based solely on its temperature. Think of a kiln, or a star, or that glowing iron poker. Here's the problem. When classical physicists, specifically Rayleigh and Jeans, tried to calculate how much energy this body should emit using standard thermodynamics, their math broke. Their formula predicted that as the wavelength gets shorter, moving into the ultraviolet range, the radiated energy should increase infinitely. Think about what that means. It means if you open your oven, you should be blasted by an infinite amount of high-energy UV and X-rays. Every time you make toast, you destroy the universe. Clearly, this doesn't happen. The experimental data showed the curve peaking and dropping off in the UV range. Classical physics was catastrophically wrong. Enter Max Planck in 1900. He was a die-hard classical physicist, but he was desperate to make the math fit the data. He did something radical. Classical physics assumed energy was continuous, like water flowing from a tap. You could have any amount you wanted. Planck said, what if the vibrating atoms in the walls of the blackbody can't just have any energy? What if they can only absorb or emit energy in specific discrete chunks? He called these chunks quanta. The energy of a quantum depends on its frequency. E equals h times f. H is Planck's constant, incredibly small but non-zero. By restricting energy to these discrete integers, 1 packet, 2 packets, but never 1.5 packets, Planck's new formula perfectly matched the experimental curve. The catastrophe was avoided. Crucial revision point. Planck didn't think light itself was localized packets yet. He just thought the oscillators that produced the light were quantized. He thought it was a mathematical trick. He hated it. But the door to the quantum world had been kicked open. 5 years later, 1905, Albert Einstein sees Planck's mathematical trick and realizes its actual physical reality. He uses it to explain another massive failure of classical physics, the photoelectric effect. The setup is simple. Shine light on a metal, and it kicks out electrons. Classical wave theory said light is a continuous wave that delivers energy smoothly over time. If light is a continuous wave, a very dim light should eventually knock out an electron if you wait long enough for the energy to build up, and a brighter, more intense light should knock out electrons with more kinetic energy. The experiments showed the exact opposite. Number 1, intensity didn't change the electron's energy. It just kicked out more of them. Number 2, if the frequency, color, of the light was below a certain threshold, 0 electrons came out, no matter how bright the light was or how long you waited. Einstein solved this by treating light not as a wave, but as a stream of particles, what we now call photons, each carrying Planck's energy E equals hf. Think of it as a one-on-one collision. A single photon hits a single electron. If the photon doesn't have enough energy, hf, to overcome the metal's grip on the electron, the work function, Badance, it doesn't matter. If a billion low-energy photons hit the metal, none of them are strong enough individually. But if one photon has energy greater than the work function, it knocks the electron out instantly. The leftover energy becomes the electron's kinetic speed. This was so revolutionary that Einstein won his Nobel Prize for this, not relativity. It proved light acts like a particle. If you still weren't convinced, Arthur Compton nailed the coffin shut on classical wave theory in 1923. He fired high-energy X-ray photons at electrons. If light were just a wave, it would just jiggle the electron. Instead, they bounced off each other like billiard balls. The incoming photon transferred both energy and momentum to the electron. Because the photon lost energy to the electron, it bounced away with a lower frequency, which means a longer wavelength. This is the Compton shift. The revision takeaway: the photoelectric effect showed photons transfer energy. Compton scattering showed photons transfer momentum. Light unambiguously behaves as a particle. So physics is in chaos. Light, which everyone knew was a wave, is acting like a particle. In 1924, a French prince doing his PhD, Louis de Broglie, asked a profoundly simple question based on symmetry. He asked, if light waves can act like particles, why can't matter particles act like waves? This is the de Broglie hypothesis. It states that any moving particle, an electron, a baseball, even you, has an associated wavelength. That wavelength, lambda, is Planck's constant divided by its momentum, p, which is mass times velocity. Why don't we notice this in daily life? Because Planck's constant, h, is tiny. For a baseball, the momentum p is huge, making the wavelength infinitesimally small, far too small to detect. But for an electron, its mass is tiny. Its momentum is small enough that its wavelength becomes significant, roughly the size of an atom. This sounded crazy until 1927. Davison and Germer fired electrons at a nickel crystal. Particles don't diffract, waves diffract. The electrons interfered with themselves, creating patterns of constructive and destructive interference. The revision takeaway: wave-particle duality isn't just for light. It's fundamental to everything. Matter has a wavelength. This leads us to our final failure of classical physics, the atom itself. Before quantum mechanics, the Rutherford model pictured electrons orbiting the nucleus like planets. But classical electromagnetism says that any accelerating charged particle must radiate energy. An orbiting electron is accelerating. Therefore, it should constantly lose energy and spiral crashing into the nucleus in a fraction of a second. Matter shouldn't exist. Niels Bohr saved the atom in 1913 by applying quantization directly to it. He didn't know why it worked yet, de Broglie hadn't come along, but he set down new rules. Rule 1. Electrons can only exist in certain specific, stable, stationary orbits where they do not radiate energy. How are these orbits determined? Bohr quantized angular momentum. He said angular momentum can only be an integer multiple of h over 2 pi. Rule 2. Radiation is only emitted or absorbed when an electron jumps between these allowed orbits. The energy difference between those orbits determines the exact frequency or color of the photon emitted. This perfectly explained the atomic emission spectra of hydrogen, those specific, discrete lines of color that classical physics couldn't explain. The revision takeaway: Bohr fixed the unstable classical atom by quantizing orbits. He brilliantly patched the old theory with the new quantum ideas, bridging the gap until full quantum mechanics arrived. Let's summarize Module 1. Classical physics broke down because it assumed nature was continuous. The fix was to realize that at small scales, energy, momentum, and even existence itself are quantized, grainy, not smooth, and that everything exhibits wave-particle duality. This was the painful, messy birth of modern physics. In the next modules, we stop using these patches and develop the full mathematical machinery of quantum mechanics. If this revision helped clarify the chaos of early quantum theory, give this video a like so other physics students can find it. Good luck with your studies.